Hello. In this activity, we are asked to find the system function and the frequency response of an FIR filter with a particular difference equation. Y of n equals 6x of n. I just noticed there is a typo because this is supposed to be 5x of n minus 1. Otherwise, you can just subtract one from the other. So this should be n minus 1 plus 1x of n minus 2. So this is the difference equation. It's a way to characterize a filter in the time domain. The other one will be the block diagram. Right? Find this impulse response. Well, the impulse response is the output when the input, so the output becomes the impulse response when the input is an impulse. So for x of n, we just place an impulse, so we get 6 delta n minus 5 delta n minus 1 plus 1 delta n minus 2. So this is the first part. A, find the impulse response. B, find the system function. The system function h of c is the C transform, right? Is given as the C transform of what? Impulse response. The same way that the transfer function in continuous time is the Laplace transform of the impulse response. So h of c, the C transform in general, and this applies to all LTI systems, not only FIR, goes from minus infinity to infinity, x of n e to the, c to the minus n, right? Which is finite in this case, and this is equal to 6, the C transform of the delta is 1, as we saw here, minus 5 C to the minus 1, where we have used that the C transform of a delay is the same C transform C to the minus k, where k is the delay, times 1, because we have a delta here, plus 1 c to the minus 2. So this is the system function. Incidentally, what we have done here was apply the C transform to the impulse response. We could apply it directly to the difference equation if we wanted, in which case we will get y of n will give us y of c, and then we'll have 6 x of c minus 5 c to the minus 1 x of c plus 1 c to the minus 2 x of c, and we will do x of c as the output over the input, and we will get the same. When you divide that, you will get the same result. This is the system function in this case, or the transfer function. C is finding the frequency response. We could compute this frequency response from the transfer function by evaluating for C equals e to the j omega hat. And so we get 6 plus 5 e to the minus j omega hat times 1, you realize, plus 1 e to the minus j omega hat times 2. This is equivalent to if we had done directly the discrete time Fourier transform and we found 6 times e to the j omega hat times 0, which is equal to 1, minus 5 e to the j omega hat for n equals 1, minus plus 1 e to the j omega hat times 2. So this is the frequency response. Now, in the next activity, we are asked to find the zeros and the poles of the FIR in the previous problems and plot them in the C-plane. And remember that in MATLAB you can do this with C-plane to plot them. And you can use the function, you can just look at the roots, right? So, in this case, x to the c is equal to 6 minus 5 c to the minus 1 plus 1 c to the minus 2 x of c, sorry. And if you equate this to 0, whether you solve it by hand or using your calculator or MATLAB, what you find is that the value of c equals to 1/2. Actually, you plug it in, you will realize that it will make it to 0, and the value of c equals to 1/3 also does that. So in this case, they are real values, real, imaginary. We have here the unit circle, okay, and so you have them here, a 1/2 and a 1/3, okay. The zeros you typically put them, that was more like the symbol for the pole. Remember that the frequency response effectively is going over the unit circle, right? E to the j omega hat. This means high frequencies, positive frequencies. This means the high negative frequencies. Why is that? This is pi, or fs over 2, the maximum frequency that you have. This, on the other hand, this will be DC, or these are low frequencies. Remember, putting zeros in the unit circle, like putting a 0 here, a 0 here, 0 here, 0 here, results, when you see this as a function of frequency, let's imagine that this is a 0, that the frequency in this application is 100 Hz. And so this is frequency of 0, this is fs over 2, so it is 50 Hz, this is 25 Hz. Okay. What we will see in this case is that as we travel around, this is 50 Hz, the maximum frequency, at 25 Hz, we had annulling over here this 0, completely null that frequency, and then you have another one right there. Okay, in this case, maybe something here also. There you go. And this is either when you're doing notch filters and you want to totally eliminate null a particular frequency that's useful, or in any filter when you see a C plot, if you have zeros in the unit circle, just remember that those frequencies are going to be eliminated. If they are close to the unit circle, whether they are inside or outside, remember that the location of the zeros does not affect the stability. It just also the zeros pull the frequency response down to 0, right? Because they are the roots of the numerator. The poles, on the other hand, these are where the zeros are going to be, zeros, roots of the numerator, poles, roots of the denominator, pull it towards infinity. And so if we wanted to have a frequency response that approximated more something like that, we will need to have some pole there within the unit circle in order to make sure that it's stable. And what the pole by itself will do will be something like that. And so the interaction of the zero and the pole will make a frequency response that is sharper. Mentioned before that although we care about the ripple in the pass band, we don't care about the ripple in the stop band as long as we met our attenuation for the stop band. As long as the worst frequency that you see there, the highest one, is still like the minus 40 dBs or 60-bit, whatever your application requires, you're fine. Thank you.